Thank you. I'm back here again. Okay, so I won't talk too much about the reasons, but of course the nasal drug delivery provides the alternate route to provide drugs, which takes away from or obviates the need for needles and the breakdown of the drug through gastric ingestion. So when we started, we got the nasal cavity, and we said, well, we know that it's definitely the design that the atomizer that produces the spray. So we cut it up and put it through the scan electron microscope, and we found these ports, and these are characteristics of what is called the pressure-swirl atomizer. And this is the physical behavior of such atomizers. So as the liquid is being pushed out of the spray, it goes through those ports on a tangential direction and creates a swirl, and through that swirl and the shearing forces of the fluid around it breaks up into droplets. So then we thought, okay, how can we define the results that we obtain through the experimental measurements and introduce them as initial boundary conditions for our CFD model? And the setup here is, to begin with, we started with a constant flow through the spray and used PIV, which is particle imaging velocimetry. And we took a lot of snapshots. This is the high speed, and then we used image processing to overlay each spray image. And this contour here shows the number of images that the droplets are shown. So out of, say, 1,000 images, then the red component shows that in all those images there was some droplet particles. And so this gave us our spray plume. And then we were able to get the velocity and found that the peak velocity of the sprays coming out is 15 meters per second. When we zoomed in to have a look at the physical behavior, we see that there is certainly that shearing effect. And these are just some images to show how it swirls around, creates this instability, and you can almost see that the wriggling pattern on the surfaces there. But of course, a real spray application is upright and is unsteady. So this is our design that we built from scratch, and there's a lot of control systems there to ensure that we can get consistent actuation of the spray. Combine that with very this is called a light shadowgraphy. So you've got light coming through one side and the camera on the other. And we'll put strain gauges on the side of the pump to ensure that to do measurements of human pumping to get the profile of the actuation, and then through the switches and the solenoids and the pumps that are coming in, we can tune the system so that it gives the same profile. And these are the unsteady spray measurements, and also in the near nozzle region. So this is right at the nozzle, and you can see again it confirms what we had before, swirling a lot. And then above that we can see that initially we went for just the same region above it, but then we realized we're missing a lot of data on either side. So we said, oh, better split that up into two sections. And so now we've got a really clear picture in each region to characterize the spray. And if we look carefully at those two images on the second row there, you can see that it indeed is like a hollow cone. So that the swirl that comes out is a cone that's spinning, and then it breaks up into ligaments, and then those ligaments further break down into droplets. And this is the interrogation regions that we put through in the 4 rows. A lot of image processing was applied, and we were able to get the droplet size distribution, and then these are critical because these can then be inputted into the CFD model as initial conditions. And the velocity was obtained through 2 snapshots of one spray pairs, so that that pair of images was had a time difference of, say, 0.1 millisecond, which then allowed us to get the instantaneous velocities. And so now we have a much better and quantified particle initial conditions. And then we put the spray nozzle into the nasal cavity and compared it with a model without the nasal cavity, and found there was some swirling effects just above the entrance of the nostril. So these are just some other patterns to let us know that, okay, maybe perhaps we do need to include the spray nozzle, because in that anterior portion of the nasal cavity, then there is some flow difference. And in the previous images, which I didn't talk about, but there was a length from the spray nozzle tip to where the ligament breakup started to occur, and we called that the breakup length. So from where the nozzle was and to where it formed droplets was the breakup length, and that region in between was just a liquid phase. So we introduced particles at a breakup length, 5 millimeters typically, above the nozzle. And we introduced them as a hollow cone, and the hollow cone coming out without any swirl, and then hollow cone with swirl. So, and while I'm here, so this is larger particle sizes, and these are smaller particle sizes. And while I'm talking about this, I could also talk a little bit about the airflow distributions and how that is created from, I guess, this almost perfectly designed nasal cavity geometry. So, for example, in the front of the nostril, you've got a 90-degree bend. And so with 90-degree bends, then you've got filtering function. So the nose is designed to filter particles out. And large particles existing in micron range will exhibit inertial effects. And so if you've got this 90-degree bend, particles larger than 20 microns will basically hit the top of the nostril. Okay? And as we move up towards the olfactory region, before the talk was talking about, the presenter was talking about how there's not much flow up there, and that's from our engineering perspective for a reason. And that reason is that you want some flow to go up, but you don't want the majority of the flow to go up, because if it transports those particles, then those particles will shoot straight into the olfactory nerves and damage the nerves. So particulate matter and particles that are dangerous filtered out through firstly the nostrils, and then that lower flow rate up to the olfactory region. But then the question is, how do we achieve olfaction? And then we have to go back to and consider what type of particle smell is, or the gases. So gases exist in the nano range, which is submicron or ultrafine particles, and their behavior is no longer inertial, but rather diffusive. So what you need then is you want a little bit of airflow to go up to transport some of those particles, and then you rely on diffusion of those gas-like particles to diffuse into the olfactory region. Sorry. So it is almost a perfectly designed anatomy to create these functions of filtration and olfaction. And then there's the last line of defense there is the nasal pharynx, where you have another 90-degree bend to filter out any other large particles that escape. Okay, so I think I have to hurry. So we then can also include the spray atomization model inside the fluent, and we use a model called LISA, linearized instability sheet atomization. And through our experiment, we can tune that model and change a few constants so that the distribution of particles that come out match the experimental data. And this is the visualization of the atomized model, and we can see that indeed is a hollow cone. And one last thing is to consider one-way coupling and two-way coupling. So one-way coupling is when the particle phase, droplet phase, moves It has no interaction with the fluid. And two-way coupling is when the two phases have affect each other. So we show here in the first box, here we've got one-way coupling. So of course the particle phase has no influence on the airflow field, so airflow field remains constant. And here the airflow field is being pushed out by the particles, so it's got a increased velocity, almost the same velocity as the spray. And likewise here, this is the momentum loss from one-way coupling and two-way coupling. So there is some difference when you have the one-way or two-way coupling modeling being used. I'll skip this. So just some future work. How can we implement so much data? Because now we have the droplet size distribution and droplet velocities. Now instead of using just the LISA model, which is essentially a black box, you input data, you get output data. And so you tune it to what you like, but rather we have a new model called the volume of fluid coupled with a Lagrangian. So you actually model the breakup and resolve the entire breakup process, and then those droplets that are formed, you transfer into another sub-model, which is the Lagrangian tracking model. And earlier I talked about the unwrapping method, and here we've demonstrated the unwrapping method and to look at the wall shear stress. And so this is the wall shear stress profile. But now that we have the spray drug delivery, the droplets then deposit onto this 2D surface, which then we can investigate further into the mucus penetration for drug delivery. Okay, thank you.